7, 8, 9, 10, 11, 12. So it will be 8 divided by 12. The new one divided by the old one.
Okay,
That's where that was coming from.
all right, and then what about this last part of this question?
All right, so that one's going to be 0.667.
Yes.
Hold on, let me put out here, because I do remember doing that one. Copy. That way you'll have it in your notes. And y'all, anytime you get stuck, go out there and look at the, so F or G was a size of 8. The original was a size of 12, and that gave me the 0.667. All right, what was the next one? Determine the probability of F or G using the general addition rule. Select the correct choice below and fill in the answer. Okay, so they want to know just the numbers. So if we're doing F and G, what was the size of this one? 2, 4, 6. 6 plus 4. And is there any overlap? 2. The size of this one was 6. The size of this one was 4. And because there's overlap, we had to take the overlap out. And they gave me 2 choices. This choice would be if it didn't have any overlap. Like if it was 1, 2, 3, and 4, 5, 6.
Mine has decimals for answers. That's what confused me because I thought it was like that, but that's not what it told me.
Let's go back to question help then.
Because, yeah, mine gave me like 0.5 plus 0.33 minus 0.167 equals 0.667.
Are they doing the 5/12 again and the 4/12? Yep. So that was 1, 2, 3, 4, 5. That was 6 over 12. Let me pull it over so we can write on our. They're taking it back to the sample space size, like we did the previous one.
So they did 6 over 12, whatever decimal that comes out to, plus the, what was the next size, like 5 over 12?
So F was 6 over 12, G was 4 over 12, and then we minus the overlap, which was 2 over 12.
Okay.
So it was going to be 0.5 plus, that's 1/3, that's 333, 2/12 is 1/6. So 1 over 6 is 0.167, and then whatever that answer is.
That gives us 667. That gives us our P of F or G.
There we go.
Okay, that makes
Yeah.
sense now.
Yeah.
Thank
We
you.
good?
Yes, thank you so much.
All right. Now, in 5-3, we're going to be doing multiplication rule and independence. Now, even though 5-3 is not going to be on your test, 5-6 puts them all together. Oh, 5-6 even isn't going to be on your test. Y'all, I was being freaking easy. That ham sandwich. Do we? What the heck? Okay, so let's go to 5-3. You're going to have homework on this, but it's not on your test. The multiplication rule is when you do 2 different things. So like if I roll a die and then I roll another die. So if I'm doing 2 different things, I'm going to use the multiplication rule. It's for independent events. Remember, independent women have nothing to do with anybody else. They don't overlap. So multiplication rules for independent events. It's independent if they don't affect each other. And then this is the rule. P, the probability of E and F is the probability that E happens times the probability that F happens. And that rule is on your formula sheet. Probability of E times the probability of F. You use this when you're doing or picking two events that don't have anything to do with each other. For example, rolling a die and rolling another die. They don't have anything to do with each other. And I've already said that independence means they don't have anything to do with each other. For example, if you eat too much and then you win a Fortnite game, those don't have anything to do with each other. Okay? Now, if you eat too much and you gain weight, those are dependent. They have to do with each other. But eating too much and winning a Fortnite game have nothing to do with each other. Dependent, and I'm hoping this is going to happen with y'all, studying for a test and making a good grade on those tests, that would be dependent. They have to do with each other. Studying for a test and making a good grade. Even though I have some of y'all say, I studied for that test and I still flunked. Most of the time, studying for a test and making a good grade on that test have to do with each other. And we've talked about this before, but I put it out there again. If you have at least $5 in your pocket, that means you have $5 or more. At least means you have that amount or more. So at least means greater than or equal to that amount or more. So if I say at least $50, that means $50 or more in your pocket. At $50 or more. I wish I have some lint in my pocket. It's about all that I have. Alright, so the first thing we're going to do is do a couple of problems to make sure that you know the difference between dependent and independent. Determine whether the two events are dependent or independent. Speeding on the interstate and being pulled over. Dependent or independent? That one is going to be dependent. Gain weight and eat fast food for dinner every night. Dependent. Get a high score on a stats exam and the Boston Red Sox win a baseball game. Independent. The battery in your cell phone is dead. The batteries in your calculator are dead. Independent. Your favorite color is blue. Your friend's favorite hobby is fishing. Independent. You're late for school and your car runs out of gas. Which one? Dependent. Okay, so either they depend on each other or they have nothing to do with each other. Alright, suppose that events E and F are independent. P of E equals 0.7, P of F equals 0.9. What is the P, E, and F? So the probability of E and F is equal to the probability of E times the probability of F. And again, you will be given that formula on the formula sheet. We did these last time. You just are plugging and chugging, making sure that you know how to use the formula. So we're going to plug this in for E. And we're going to plug this in for F. We're going to multiply those two together. And we're going to get our answer of 0.63. So the probability of both of those events happening is going to be 0.63 or 63%. All right. About how many of y'all are left-handed in here? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So she is 1 out of 14. Let's see how close it is to this probability. 7%. So 13% of the population is left-handed, 7% of this room is 7% of our sample is 7% of our sample is left-handed, but 13% of the population is left-handed. If two people are randomly selected, what is the probability that both are left-handed? So it's like I'm reaching in and I want to get a left-handed, and I'm reaching in and I want to get a left-handed. So I want to know what is the probability of a left-hander times the probability of a left-hander. So what I just did is I said, what's the probability of a lefty and a lefty? So I'm using that same formula. The probability of a left-hander and a left-hander is the probability of a left-hander times a left-hander. So what's the probability of a left-hander? 13%, but we use it as a decimal, so we got a whoop-whoop. 0.13, and the probability of a left-hander is 0.13. So we're going to do 0.13 is the probability for the first person to be left-handed, and 0.13 is the probability for the second person to be left-handed. And if I go to my calculator, I can either do 0.13 times 0.13, or I can do 0.13 squared, because there's two of them. Does not matter, it'll give me the same answer. So the probability that I walk into a room or into the world and I ask two people in a row, are you left-handed? Are you left-handed? The probability that that's going to happen is 1.69%. Is that probability unusual? Why is it unusual? It's less than 5% or 0.05. Very good. Now, have y'all ever had Christmas lights where you pluck, like one light was bad and it made the whole string go out? Back in the day, that's how Christmas lights, or sometimes still today, that's how they are. One bad light or one that's out makes the whole strand or makes the whole sequence go bad. So that's what this is talking about. Christmas lights are often designed with a series circuit. That means that one light burns out, that entire string or that entire, like maybe every fifth one or every third one is going to go out. Suppose that the lights are designed so that the probability of a bulb will last 2 years is 0.995. The successor failure of a bulb is independent of the successor failure of other bulbs. So the probability that, or the successor failure of this bulb has nothing to do with the successor failure of these bulbs. They are all independent. What is the probability that in a string of 100 lights, all 100 will last 2 years? So I want to know the probability. What's the probability that this bulb will last 2 years? 0.995. What's the probability that this one will last 2 years? What's the probability that this one will last 2 years? What's the probability that this one will last 2 years? And I'm going to do that 100 times. So for part A, I'm going to do 100 bulbs. And the probability that it's going to last is going to be 0.995. And the probability that this one's going to last is 0.995. And the probability that this one's going to last is 0.995. And I'm going to do it all the way until 100 times. So the probability of 100 of them lasting is going to be 0.995 to the 100th power. Yay? Good. Now, if I go to my calculator, let me see what it'll give me. 0.995 to the So we have about a 60% chance that all 100 bulbs are gonna make it 2 Christmases.
That's wishful thinking.
Do what?
That's wishful thinking.
That is wishful thinking. Usually we just buy every year. So it's almost a little over a 50-50 chance that you're gonna make it every year, which is saying, and if you have to put 2 strands on, you're screwed. What is the probability that at least 1 bulb will burn out in 2 years? Because if 1 bulb goes out, 1 bulb, what's gonna happen? All of them gonna go out. Now, what did I tell you yesterday? Monday, if y'all can remember. What did I tell you Monday if I say at least? What do we do if I say at least? If I tell you at least, you're going to do 1 minus. Now, we've got to figure out, we're going to do 1 minus what? We're going to do like the not. So if, yeah, you're right. If they burn out, that means like 1 would burn out and the next one would burn out and they would all be on, the next one would burn out and they would all be on. So we've got to take it down. So what can it not be? What's the only thing that we wouldn't like? There's a lot of things that would make us happy. The first one out, the rest are working. The second one out, the rest are working. Third one out, the rest are working. Fourth one out, the rest are working. But what's the only thing that would not make me happy? All of them working, right? So if I take out all of them working, then everything else would make me happy. So if I take out all of them working, then what's left is everything that I want. It's the complement. Like if I take out all the pregnant people, then what's left is all the not pregnant people. So if I take out all the ones that are working, then what's left are the ones that are not working. So, how many were working? 0.606. So if I take out the 0.606, then the rest are going to be all that were not working. So, and I don't like to round, so I'm going to do 1 minus 0.995 to the 100th. So I'm taking out the working ones, and that's going to give me the not working ones.
Oh, this makes sense.
I saw your light bulb just come on. So I'm going to do 1 minus 0.995 to the, everybody else is going, I wish my damn light bulb will come on. I'm in that one that's not working. So the not workings are going to be 0.394, whatever they tell me. Because I can't take into account, well, what's the probability of this one not working? What's the probability of this not working? So I've got to take out all the ones that are working to give me the ones that are not working. That's why when it says at least, that's going to be everything else, the rest of the story. I'm going to do a lot of these, I promise. And did I say if these were on the test or not?
Is this where that like the power to the sea come from? Okay.
All right, let's look at, those are the answers. These are the answers written out pretty. All right, let's do another one. The probability that a randomly selected 40-year-old male will live to be 41 is 0.99757. What is the probability that 2 randomly selected 40-year-old males will live to be 41? So, I want to know for part A, I want to know the probability that I want to make it to 41, and I want to know the probability that I make it to 41 again. So what's the probability that the first dude lives to 41? The 0.99757. And what's the probability that the next dude lives to 41? 0.99757. Now let me see what that answer is. 0.99515. So if I find two dudes in a row and say, what's the chances that you're going to get to 40? Y'all, most people are going to live from 40 to 41. Now, if I was going from like 89 to 90, this isn't going to be this high of a probability. But most people live from 40 to 41. The chances are high that you're going to find two people that live from 40 to 41. What is the probability that 5 people live from 40 to 41? How would I do that? 0.99757 to the 5th. Because it would be 99757, 99757, 99757, 99757. So I'm just going to do 99757 to the 5th. Because I'm lazy. 0.99757 to the 5th. And that's going to give me 0.98791. What's the probability that ding, 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 ding? So what are we going to do? 1 minus. Now, we want to find the people that will not live. So, the not lives are going to be 1 minus the
0.99757.
987.
the living. 1 minus the living's going to give me the not livings. 1 minus the pregnants are going to give me the not pregnants. Now, but we're doing 5 of these people. So what am I going to have to raise this to? To the 5th power. Because we got 5 of these yahoos. So because it's to the 5 random men, I'm going to raise it to the 5th power. So it's going to be 1, oops. Come on. It's going to be 1 minus 0.99757 to the 5th. .01209. Would it be unusual to find?
Yes.
Yes, because it's less than 5% or 0.05. And again, I have them written prettier down here. But I don't want to show you that when I'm doing them because y'all cheat. I don't trust you. All right, let's get into a little bit of sports. Players in sports are said to have hot streaks and cold streaks. A batter in baseball may be considered in a slump or a cold streak if he has 10 outs in 10 consecutive at-bats. Now, for those of you who don't know about sports, if you walk up to the base, to the home plate, and you are up there, that's called an at-bat. You walk to the bat and try it, and then you get out. So if you walk up 10 times and you get out 10 times, you suck at the moment. You got a 0. 10 for 10. You are 0 for 10. Suppose that a hitter successfully reaches base 30% of the time he comes to play. So 30% of the time he comes up here he goes to the first base. So that means what percent of the time does he head back this way? 70%. So this right here, they didn't tell me that. Well, they did right here because they were nice. So 70% of the time he heads back because the 30 plus the 70 are complements of each other. Now, find and interpret the probability that the hitter makes 10 outs in 10 consecutive at-bats, assuming that the at-bats are independent events, meaning they have nothing to do with each other. So, let's come down. So, for A, I want to know the probability of 10 at-bats getting outs. So the first time he walks up there, he gets an out. The second time he walks up there, he gets an out. So if I put it out like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. He gets an out, 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 he gets an out. So what is the probability of him walking up the first time and getting an out? Not everybody at once. 0.7. Because there's a 30% chance he's going to make it to the first base. There's a 70% chance he's going back. And I just told you, he's going back. So 0.7. What's the probability he's going to get it out next time? Next time. Next time. And how many times are we going to do this?
10.
So this is going to be 0.7 times 0.7 times 0.7 times 0.7 times 0.7 times 0.7. So this is going to be 0.7 to the 10th, which gives me 0.02825. Are these cold streaks unusual?
Yes.
Yes, because it's less than 0.05. Find the probability that the hitter makes 5 consecutive outs, then goes to first base. Now, for me, sometimes I have to draw that little picture. So, probability of 5 outs, then he goes to first base. So, how many times does he go up there to home plate? 6. He got an out, 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 and then he got some action. So what's the probability of the first 5 outs? 0.7, 0.7, 0.7, 0.7, 0.7. And then what's the probability that he made it to first? 0.3. I got to physically see those numbers out there. So what is my mathematical problem going to be? 0.7 to the 5th times 0.3. So the 0.7 to the 5th represents the 5 times he had to do to walk a shame. The 0.3 is the 30% chance that he made it to first base. And that is going to give you 0.0504. Said that was B, but that was actually C. How we feeling? They're easy when I do them, right? And for these, you may have to hit that view an example button. Okay, I am not a bowler. Do we have any bowlers in here? Bowlers? Travis is a bowler. Do we know what a strike is? Strike's when you knock all the pins down in one swoop. Ralph gets a strike when bowling 30% of the time. So 30% means he's kind of good. 30% of the time, knocks him out. Strike. Now, they didn't tell us this. But what percent of the time does he not get a strike? So 70% of the time.